Hi, and welcome to this first video from the Year 2 content on forces. And what we're going to do is start building just slightly more complex models of how to deal with forces in slightly more difficult situations, built on the ideas that we learnt in Year 1. So first of all, we're going to be looking at how we're going to start resolving a force into two components, into two different directions. So here we go. So if a force has been applied at an angle, then we need to resolve it to find out how much force is going in each direction. In Year 1, we just had forces just going in one direction. Now we're going to have things going in a couple of directions. So here we go. So we've got a book sitting on the table, and what we've got is a force that's going to be applied to the book that's going to drag that book along the table. So now, how much of that force F newtons is going, how much of it is going upwards, and how much of it is going horizontally? We've got the two parts of it. The bit that's trying to drag it along the table, and the bit that's essentially trying to lift it off the table. Right, clearly how much is going in which direction is entirely dependent on the angle. Clearly if you decrease the angle, then more of it's going to be going horizontally. If you increase the angle, then more of it's going to be trying to lift the book off the table. And here's an idea that hopefully you should be reasonably familiar with by now. If we have a look at that triangle, we've got a force that's the horizontal component is going to be x over f is cos theta, so that's our basic trig. Bit of rearranging, so we've got our x component of the force is going to be the size of the force times by the cos of the angle. And similarly in the y direction and the vertical direction, we've got the same thing going on. So those are our two bits, and that is going to be something that's going to be repeated and recurring over and over and over again throughout this section, those two ideas. The horizontal component f cos theta, the vertical component f sin theta. Now, having said that, I am going to add a little addendum to what I've just said. I was teaching from this PowerPoint a couple of weeks ago. One of my students said, well, hang on a second, sir. Is it always cos for horizontal? Is it always sine for vertical? Because in physics, we're told sometimes it's the other way around. And he's absolutely right. It does depend a little bit on which angle you're referring to. So I'm just going to do a little bit of scribbling. So, well, let's say we were working with that angle there, in which case our triangle would now be there, and so our horizontal force in that direction would clearly be the opposite. So in that case it would be F sine alpha, and the vertical force, let's pick a different colour, the vertical force there would be F cos alpha. So it does depend on which angle you're dealing with, but generally speaking we have this angle under here. So it does tend to be that way around, but let's say you just have to watch out. It depends on which angle that you're working with. So let's just get rid of all of that and crack on. Right, so let's say now we've got the book's got a mass 2 kilograms. It rests on a smooth horizontal table. So find the reaction force of the book on the table, and then we're going to change things when we've got a force of 10 newtons being applied to the book and see what happens. So there's our basic setup. So there's our book sitting on the table. And so let's just think about all the forces that are acting on it. Well, initially, we've got a reaction force there, and we've got the force due to gravity there. Those are the only forces that are going on. So therefore, we've got our reaction force is 2g, which is 19.6 newtons. All very straightforward. And let's just now have a look at what happens when we put this extra force in place. So here comes my diagram again, and now I've got the additional force going at a 50-degree angle. So what impact is that going to have? Well, first up, the reaction force, if I resolve it in the vertical direction, so what I'm looking at is all the forces that is going upwards. So I've now got my reaction force, and I've now also got the vertical component of my 10 newton force, which in this case is going to be 10 sine 50. And so those two forces combined are going to be equal to 2g. So now what's happening to the reaction force? So if we just rearrange that to make it say R equals, we can see our reaction force is going to be decreased because of the result of those forces, and that's going to have an impact on things like friction, all kinds of stuff later on. What's going on with the acceleration? Well, to work out acceleration, because now we've got this box, the book was originally motionless, now we've got a force that's going to be partly trying to lift it off the desk, but also going to partly come and try and move it across. So the acceleration, let's resolve this in the horizontal direction and see what we've got. Well, if we use F equals ma, what force have we got acting horizontally? Well, the only bit we've got acting horizontally is our 10 newton force or component of it, which is going to be 10 cos 50. So that 10 cos 50 equals mass, which is 2, times by acceleration. So the acceleration is 3.2 meters per second. So that force is going to cause that book to accelerate along the desk. Okay, so on we go. So we've got another example here where we've got a mass attached to 2 separate light and extensible strings. As ever, strings are always light and extensible in mechanics models, so no mass and they don't stretch. And the particle hangs in equilibrium, and we've got to find the tension in each string. Right, first thing to note is that because we've got 2 separate strings, then we've got 2 separate tensions. If we had just, for example, a ring being threaded onto a single string, you could have the same setup, but the tension would be the same in both. But because it's 2 separate strings, we've got 2 separate tensions. Okay, so I'm going to call those T1 and T2. And I'm going to put my forces as they apply to the mass at C. So we've got gravity here, tension in the string there, tension in the string there. And what I've done is just included a couple of angles there just to help us along. So if we start resolving in the vertical direction, let's see what forces are being applied in the vertical direction. Well, we've got T1 cos 45. Again, I'm looking at a triangle here. So the red line is the adjacent side, so it's cos 45. And we've then got T2 cos 30 for the same reasons. And it's in equilibrium, so the vertical forces upwards equal vertical forces going downwards, so that's mass times gravity. And so there we go. And all I'm going to do now is just include the values of cos 45 and cos 30. Cos 45 root 2 over 2, cos 30 root 3 over 2. Now let's have a look at what's going on horizontally. And so what we've got is T1 sine 45. So again, looking at this triangle here that I'm tracing out, I'm going in the direction to the left, so it's going to be opposite to the angle, so it's sine 45. And because it's in equilibrium, that force going leftwards is going to be the same as the force going right, so that's going to be equal to T2 sine 30. And again, tidied up a little bit with our values for sine 45 and sine 30. And the reason that we're going to need to do both here, we've got 2 equations, because we've got 2 variables, we want T1 and T2. So now we're in a situation where we've got to do a simultaneous equation. So a little bit of rearranging, so we've got T2 equals root 2 T1. And so now what I'm going to do is just plug that back into my equation, which is this one here. So T2 I'm going to replace with root 2 T1. So there's the substitution. Now we've got an equation that's just in terms of our only variable T1, because remember M times G are in this context fixed, so we can't do anything more with those. And so now what I've got to do is just make that say T1 equals, and because it's a year 2 video, I'm sure you're all more than capable now of kind of doing the manipulation. I've missed out those stages, I'm just going to jump straight to the answer, and there we go. T1 is root 6 minus root 2 over 2 mg, and once I've got T1 sorted, I need to go back and sort out T2, which is going to be that, which is simply root 2 lots of T1. So I'm just going to stop this video there now before we move on to more complex models, and particularly with things moving and friction, all that kind of stuff. But it's just a case of making sure we're happy about how we can split a force into 2 different components, horizontal and vertical.